Hello and welcome back to another coding session with Mr. Jacob. Today we will implement dithering in Rust. So what we want to do is we want to open up some sort of image. We want to dither it using maybe Floyd-Steinberg or something like that. And then we want to output that image. I need this because I have some of those e-paper display frames I have built in my home. And as you can see, I have or as you can see here, I have some that can display even color, and though they can display 7 different colors. And I want to dither those images that I got, and I want to do that in Rust to be displayed on this ink frame here later on. So what I want to do is to implement that for now by just taking and loading up an image and doing that, and then later on I may even integrate that into further projects. The interesting part here is I have already done that quite some time ago, in a hackish way in JavaScript, and I now want it in Rust because I want to incorporate it maybe into a server, which will then work and create those ditherings live for me as I am sending the images over to the picture frame. So yeah, so that is what we are going to do today. So let's get started, I guess, by, let me close this one, and let's get started by maybe taking a look at how we can open up the image. As you can see, I have an empty folder here, so let me quickly do a cargo init. And the way to handle images in Rust is actually the image rs library. So let's add that. And let's add anyhow as well, because we will be going to do error handling, then we have that in there as well. Let's go over to Visual Studio and let's take a look at the main rs, which should be here. There it is. Perfect. So let's first of all go ahead and parse some arguments. We can take them from sysenv, if I remember correctly. So let args env args, I guess. Yeah. So this should give us the arguments, and now I guess we want something like command args unresolved. Wait, what? Oh, it's stdenv, not sysenv. Thank you for Visual Studio for catching that. We want to actually cut off the first one, which is always the command. So let's see, args, wasn't there a shift size slice first or something? There is something like chunk slice. Wasn't there something like oh wait, I guess args is an iterator, isn't it? Yeah. So let's quickly collect those into a vector of strings. And now args should have something like, yeah, split. Returns an splice, split add, split first. Split first is what I want. So this is actually, and this might return an option because there mustn't be, or there could be no entries in this array. So let's see, but we expecting to always be provided at least the command within args, something like that. So okay, so now we should have the rest of the args plus our command. So now we can check if args.len is less than 2, because we want an input and an output, then we will simply do an eprint line usage eprint line something like command and like input.image or input image and output image, something like that, I guess. Yeah, and then we will simply do, is it std process exit. I seem to not be able to type today. So, okay, so let's do that, and then let's just print line, maybe args. Let's do the debug print of that. And let's maybe simply try and run this. Run, and this should actually, oh yeah, it needs, of course, to compile now all the stuff anyhow, and especially the image. The image library is quite the dependency. As you can see, it has a lot of sub-dependencies there. But luckily, we only need to do this once while working on this project here. Hopefully. And this is a lot slower when I'm recording a video. But yeah, let's see. So yeah, okay, this worked. So let's see with one argument, in.jpg, something like that. Doesn't work. Out.jpg. Yeah, okay, I put there JOC and not JPEG, but yeah, it works. Okay, that's already quite nice. So now let's see, how can we actually open up image RS docs? How can we actually open an image? Okay, it seems we can just call the image reader open and decode, and then we get some sort of image. That would be quite nice, actually. So let's see. First of all, I've already seen that this one returns a result, so let's do quickly a result with an empty set here and use anyhow result and context here. And yeah, of course, and you need this one there, and this one goes away. So yeah, this should actually work then. So let's do something like let image, maybe scroll this up a little here. What was it now? It was the image reader open, and yeah, maybe we can do something like let input equal args 0 here, and let output equal args 1 here, and let open the input here, and we can actually add a context, something like open image input for reading, and image reader. Yeah, I guess we need to import that. Wait, no? Use, where actually does it? Image IO reader. Oh, I see. Yeah, okay. Image IO. Yeah, but then I don't like that. I don't, no. Then let's do an image IO. I get why they didn't want to call it reader, but no. Okay, yeah. Okay, cannot move out of type. Yeah, but you don't need to. You can reference that. I'm perfectly fine with that. So now this should do, and then there was this, what was it, decode. I guess this is actually then reading the image data. So like decode input image input, just in case that fails. So yeah, and I will comment this one out here because we won't maybe not need it for quite some time, or maybe we will, we'll see. So yeah, maybe I will leave it in because that will be the next thing we do. We read it and then we kind of try to write it again, and we will see how this works out. Okay, so now we might have something like, what is it? A dynamic image. Okay, I see. What is a dynamic image? Because I would love to have a byte array. Dynamic, there it is already. So, okay, it seems there are all kinds of different image types there. Yeah, that kind of makes sense. But can I somehow dynamic array into? Okay, so it seems you can convert those things into specific new. Is there something like 2 RGBA 8 or something like that? Returns a copy of this image as an RGBA image. Okay, I see. But there was an into as well, wasn't there? Because essentially I don't, yeah. Consume the image and return. The image was already the correct format, is returned as is, otherwise copy is created. Okay, this makes sense actually, because we don't need it in its original form, and maybe it will save us some RAM. So maybe we can actually do that directly here. So why not? We can do into RGBA8. Attempt to take value of method on dynamic image method, not field. Wait, what? Oh. Yeah, let's see. Yeah, okay. So now we have an image buffer. Okay, nice. So the question is, how do we get an image? We have an image buffer, I see. So image buffer, image buffer, image buffer, image buffer, there, image buffer. So, okay, this is kind of put pixel. Okay, we could actually work with that, but I would actually think I want to work returns the underlying buffer. So let's do the following. Let's try something like buffer is image dot as what was it? Raw buffer as raw. And now I should be able to do something like maybe buffer, or maybe I guess we need mute here. And oh, can we will see, because I guess this will not work. So if I do this and I want to change this byte to 255, will this actually work? No. Yeah, I guess this will not work like that. Is there maybe something like no. Is there something like into raw? Okay. I guess we can do that. So let's do the following. Let's actually do the following. Let dimensions, I've quickly glanced at that while scrolling over. No, let's width and height image dimensions. So we definitely need those. And now, what is it if I do into raw? Even though I'm not sure about the stride and something like that. So now let's do something like, now I should be able to say it's mutable because I own this thing now. And now I should be able to do something like buffer 0 should be 255. Buffer 1 should be 0, and buffer 2 should be 255, and buffer 3, which would be the alpha channel, should be 255. So now we should have maybe a magenta pixel in the upper left corner, not 100% sure. And let's see. Yeah, let's now try and save this thing. Can we do something like that? Oh wait, we now have a pixel thingy there. So I guess we need something like right to, no, that's for an image, don't they have something like just, do I need to create a new save buffer? Saves the supplied buffer to a file and sparse path specified. Oh, that looks promising actually. So save buffer, sorry, gets a path, a buffer with height and some sort of extended color, whatever. Oh yeah, I see. Okay, this is just the, yeah, okay. So image, save buffer, output, then the buffer with height, and what was it? Extended color type, that would be RGB A8. And I guess, we should do something like dot context, saving image to out, save image to output. To output. This is the way I wanted to do that, and put a question mark there. So, okay. Okay, so now we should be able to, let's check if this builds, but it should, I guess. There were no compilation errors, there are no indicated errors. So yeah, and I guess now let's grab a something like a picture. What about this one? This one looks nice. So let's quickly download that. Actually, how was that called? Yeah, I guess the penguin, okay, I see. So let's move from my downloads folder, do something penguins yes to just input.jpg. And now I guess we can do something like cargo run input JPEG to output JPEG. And let's see. The encoder or decoder of JPEG does not support the color type RGB88. Okay, that makes absolute sense. So let's write it as a PNG. But actually, maybe we don't even need this alpha thingy stuff. Why bother with it when we don't even need it? But let's for now see what the output PNG actually does look like. Okay, that looks like the, yeah, that seems to be the original image. And do we have, yeah, nice. Let me zoom in even further, because now this seems to have worked. We have actually a magenta pixel up there. Okay, so now we can actually open an image, read it in, and save it out as a PNG. Yeah, let's remove this alpha channel, because why bother with it? We don't even need it. I guess there is an RGB8 struct, and we can write out this as RGB8. So I guess this should do the same thing then. Let's see. Okay, so open output PNG. Yeah, looks okay. So is there still? Yeah, there is a pixel there. So that worked out. So, okay, nice. So now we can actually open an image and we can save it and we can access it as a byte buffer, which is more or less exactly what we wanted to do first. So I guess this can all be a little bit more compact here. And maybe call this, we can maybe call this buffer. Buffer is, I guess, a nice enough name. So now we need to implement dithering with error diffusion, like in Floyd-Steinberg, for example. So let's see, Floyd-Steinberg, and let's see, there is definitely a Wikipedia entry. Yeah, Floyd-Steinberg dithering. So dithering actually is dithering with error diffusion is something like we have this picture, like in an example. Okay, you can't even really see that because it's on the right side where my my faces. So now this should actually, maybe even, we can do this even a little bit smaller. So actually it's something like you have this photo here with a lot of different colors and you want to reduce the color set, or you want to map to a specific set of colors or something like that. So what you could do is you could map naively every pixel to its nearest counterpart in your desired target. But this will create this evil color banding here, where you have this hard transitions between colors, and it overall doesn't look very nice. But our eyes actually are capable of kind of interpolating between colors. So if you go ahead and use your existing colors in some intelligent way to make it look more like the original seen on a wider spectrum or wider space around it, then it will look definitely a lot nicer. And this is actually possible using so-called error diffusion. So what we are doing here actually, let me make this full screen again. What we are actually doing here is, instead of plainly mapping to the new color, which we will need to implement as well, we are going ahead and diffusing this error. So we will be using we will be calculating the quantization error. So the error of calculating this this difference between the original color and the new color, and we will then put it to the surrounding pixels. So this is actually the pixel that is quantized at the moment, and then the one to the right will get 7/16 of this quantization error, and the pixel below that get other values there. So it's exactly like in this matrix, and there are different matrices by different people for different use cases, but Floyd-Steinberg is usually working quite well. There are some others there, but once we have implemented that, we can easily implement the other matrices as well. But before we even get to that error diffusion here, to this, and as you can see, this is, for example, a quantization with only using black and white, and this is quite impressive actually, how this actually looks, even though there are only black and white pixels in there. So yeah, that's quite nice. So, but before we can even implement error diffusion, we need to map to a specific palette. So let's do that first with our picture, I guess. So like, maybe we can Google something like 16 color game palette or something like that. Generic 16 color, this looks nice. So yeah, this is it seems to be a quite nice palette, 16 color palette. So, oh, nice. So let's take this and let's first of all somehow represent that. I guess what we want is something like a color struct, don't we? So struct color, and color will be then an R, which is a U8, and it will be a G, which is a U8, and it will be a B, which is a U8. And then we definitely want something like color, no, impl color from, I guess from a U32, so that we can actually put it in there in a hex way. Yeah, why not? Let's and it's no, it's for, oh, it's actually from U32 for color. Well, what have I been typing there before? It doesn't make even any sense. So are all traits implemented? Yes. Yeah, that's what I just wanted to do. So this is the value here. And so let's implement this one, I guess. So I guess what we need to do there is we take, I'm just thinking about which parts of the value we are using. I guess we will use them from right to left. So let's, yeah. Okay, so what we actually want to do here is we want to return a color. We have, let's put them here in different order, B, G, and R. because the least significant bit will be the blue color, the green color will be the second one, and then the most significant bit, or not the most significant bit, but the third 8-bit group will be the R color. So let's see. The easiest way to do this, of course, would be to just end this with with 1 byte. So we should now have this one there, and okay, so yeah, then we can convert it into a U8, and this should fit. Mismatch types, expected. Wait, what? But didn't I just tell you to make it a U8? Okay, interesting. I need to... Oh, okay. Yeah, and we need to shift this one like... we need to shift this one 8 bits to the right, and then end it with FF, and this as a U8. And for the R, we need to do more or less the same, but we need to shift it 16-bit to the right and do that. Yeah, this should actually convert our U32. And now we should actually be able to do something like maybe in between here. Let's do let palette. I never can write palette, which is a vector of colors, I guess. And no, and this should be vec. And now we should, I copied this already, but I've in between emptied my copy buffer. So let's put that there again. And let's put those there. And now let's see. We can first of all remove all of that. And here we can remove all of that. And now what we want to do is we want to put something like color from 0x in front of this, and I guess we want something like this there. Okay, now we should actually have all of our colors in the palette. So what we need to do now is we need to, for y in 0 to width, I guess, 0 to height, it's y, it's not x, so 0 to height. For x in 0 to width, we want to iterate our data buffer, so the actual index which we are iterating there should then be y times the width plus x, and this complete thing here times 3, as we have 3 bytes per pixel. And this should actually be the index in our color buffer. So what we can now do is we can say buff I should equal map to palette, and we give it a reference to a mutable reference to our buffer, I guess. No, wait. No, it already returns this. So it's just, we give it the buffer and we can't buff. We called it buffer, didn't we? So let's see, buffer, yeah. And yeah, and this needs to be a U size. I see, as U size. And we give it a reference to the palette that we want to use, I guess. And what this method then needs to do, we don't have that yet, but let's quickly implement that. Fn map to palette should take in, yeah, what actually is it then? It is it takes a slice of, maybe we should convert that. into a color. So maybe we should implement something like, because we are getting actually a slice of 3 U8s there. So maybe we should do something like from, can we actually implement that? I've never tried that. Can I do something like U8 3 here and then for color, and can I implement that? It doesn't complain, so yeah, maybe we can actually implement that. So let's do so, I guess. Color R would be V0, G would be V1, and B would be V2. Yeah. So now what we can do is we can actually, there you go. You can actually do buffer. We can actually do color from buffer. Oh, it's I to I plus 2, I plus 3, because it's exclusive, isn't it? So expected 0 arguments found 2. Yeah, okay, we didn't have, we haven't implemented that yet. And actually we need, of course, to reference that one there. And now I guess we can take a color here. Come on. We can take a color here. So let's call it OC for original color, or let's call it orig as a color. And we take a reference to a palette, don't we? So we take a palette reference, which is a vec, and it's a reference to a vec of color. And we return a new color. Yeah, and as I don't want it to scream at me, I'm putting a U to do there. And now there is something still wrong here. The trait bound color from is not okay, so it doesn't know that this thing has a len of 3 then, I guess. That's interesting. It should be able to infer that. I would have guessed that why can't it infer that? But yeah, okay, maybe we can just do something like that. And something like that. And it will then crash if I'm retrieving an index here which does not exist. Is this now okay? Mismatched types. Expected U8 found color. So yeah, this would be the return type actually. Yeah, that is right. So I guess I will have something like new here for new color, or yeah. And then I would do something like buffer buffer I equals to new R, buffer I plus 1 equals new dot G, and buffer I plus 2 equals new dot B. So yeah. Okay, so this seems not to work, so let's go ahead and implement palette. Actually, the easiest way to implement that, or the most common way to implement that, is that you do a nearest neighbor search. We are searching for the nearest neighboring color to our original color, and we are doing this simply in 3D because a color component, a color consists of 3 components, R, G, and B. And what we can actually do is we are treating them as X, Y, and Z coordinates and are simply searching for the nearest neighbor from our color to that target color. And there are fancy ways to optimize this, and in some cases this even is a quite good idea to do that, to limit the search space and stuff like that. But for the quite low amount of colors that we are going to check here in our use case, it is perfectly fine, and usually even the fastest way then to just do a linear scan and walk through all of the palette colors and take the one that has the shortest distance. So let's quickly implement that. Let's implement that by doing something like, first of all, we need the minimum distance that we have seen so far, which would be, let's do a Q32 infinity for now, for the beginning, and let's mark the selected color, which would be, I guess, by default, simply the a reference to the first color in the palette. And let's put it to do here again, because I don't want all those errors. There are enough anyways. So yeah, so now that we have that, we can actually do for candidate in palette. I want actually to do something like, I want to check the distance to our color. So the easiest way to calculate that, of course, is by using the usual algorithm, and then by squaring all the differences up, and then using the square root of that as a distance. But as we are only interested in the relative distance changes, so we are interested in what is far away and what is nearer to our color, we don't need to take the square root actually, and can save up on some calculations there. So what we actually want to do here now is we want to do let distance equals, and now we need to do some type comparisons, I guess. So we need color.r as f32 minus candidate.r as f32, and I guess we want to do powi2 here, and those we want to add up. Yeah, I guess this will the way to go. And I will quickly copy that and just put it there, before then quickly doing a B here, a B here, a G here, and a G here. And now we should have actually calculated the distance. And now if distance is smaller than min distance, then our new selected color, and we need to, I guess we need to make this one mutable here. Our new selected color will be the candidate. Yeah, I guess so. And wait a second, what we need to do here is we need to set the new min distance, of course, because the new min distance is the distance in this, then this thing here will have to be mutable as well. So, and in the end, actually, once we done that, we should be able to just return our color. But wait, this is a color reference. So yeah, why not return the referenced color from the palette? Wait, why didn't we use... Wait. We did something wrong here. Oh, all of those should have been called oric, of course. I guess you all have been screaming to you, onto your screens for me to use the correct one there, but I didn't. So yeah, so this actually seems to be okay. So I'm quite irritated. I like it, but I'm quite irritated why I didn't have to provide a lifetime specifier here. But maybe because we only have one reference here, and it then can determine or infer that the lifetime of this is bound to the lifetime of this input. Okay, so what we have now actually, if we run this program, should be a simple color mapped output of our input. So let's take a look at that output PNG. Yeah. And as we might have guessed, it worked. It mapped cleanly to our color palette, as we can see here. But it looks quite horrible. So this is this bad color banding, and here down in this this area, and mostly everywhere here, that doesn't look good. So let's see how we can make this better. The but at least this works out so far. Yeah, so now we have that. We have mapped that to the palette. What we now need is the quantization error. So to diffuse this error according to this Floyd-Steinberg matrix, or to using any other dithering and error quantization error diffusion system, we need this error. So we need to change something here in map to palette, because we need to return the error as well. So let's see. I guess we will now return a tuple. We will return the new color, and we will return some sort of quantization error, maybe? Maybe we will need to define that type. Yeah, I guess we will define that type. So simply do something like struct quantization error, and it will have an R, which is a F32, a G, which is a F32, and a B, which is a F32. We could have made color generic for that over the type it can store, but no, I don't think so. I don't think so. I think this is it's okay. So let's do something like return the color and some sort of quantization error here now, and we need to take a look at how to calculate that. So let's calculate that. Let QE. And QE should be a quantization error. Quantization error in R would be the difference between the original color, where is it? What did we call it? Orig. So oric R minus our new color, so like our color, so color R. And yeah, of course we need to do as F32 here, as F32. And then there are the G and B fields, which actually have exactly the same, G, B. G, B. And you might be asking, expected function found quantization error. Wait, what? Why was a function? Okay. You may be asking yourself, why am I doing this as a float? Because something like an isize or even an I32 maybe would have sufficed here. But we are going to multiply this value with floats going on, so I can easily store them as F32 as anyways, as I need to convert them because this value might be negative. So I need to switch the representation around anyways, and I need to duplicate these values here anyway, so I can do that as a float anyway. So I'm now returning this, so I need to, I guess, reflect that here. So we have the new color and we have the quantization error. And now we need to do the error diffusion part. So now we are going back to, where were we? Floyd-Steinberg there. Now we are going back to this matrix here. So it's a 2 by 3 matrix. So it's 2 rows, 3 columns. And yeah, I guess we can define it here for now. Let's wait. Let's just do a let Floyd-Steinberg or something like that, and let's create that as a new vector. Of vec of 32-bit floating point values. So, and as we are ignoring those actually, but we will be iterating them for the sake of simplicity in iterating, we will actually put them there with 0.0, 0.0. So this value and this value will both be 0 because 0 of the quantization error will be put into those pixels. And then we have something like 7/16. Okay. And now we have 3/16. We have 5/16. And we have 1/16. And it says now mismatch type because I made a comma there instead putting a point, and there as well. And this works, and now if I reformat it, it makes it into one row. Okay, but I don't have a problem with that. So now we have those values there. What we now need to do is we need to more or less iterate those new pixels. So what we need to do is we need to do something like for, let's call it delta y in 0 to 1, including, do something with the y coordinates because we have 2 rows, and for dx in -1, we want 1 to the left and 1 to the right, to including 1, do something for x, and now maybe we should rename those here cy and cx because they are actually the center coordinate, and now we can calculate new x's. So x is now cx plus dx, and y is actually cy plus dy. Oh, wait, -1, trade bound U32 not satisfied. Okay, this will be an I size. I see. So I need to do something like as I size. As I size here. Yeah, okay. And now we need to do some sanity checking. So if x is smaller than 0, or x is bigger or equal the width, or y is bigger or equal than the height. It can't actually be smaller than 0 because we are only adding to it. The dy goes only from 0 to 1. So then we want to simply ignore this pixel here. And what is it complaining about there? I should have put an if there, not a let. Okay. So mismatch types. Yeah, I guess so. So as I size. Okay. Now we are sure that we are still inside the image. And now what we need to do is we need to calculate the new index. So we can actually take this from here and simply replace the cy and cx with x and y. And now this won't work because x might actually be negative, but at this point we are quite sure it isn't. So wait, we are sure it isn't, aren't we? So we can do as, what is actually this value here? It's a U32, so we can do as U32. This is actually fine. It can't overflow because it isn't negative. We are sure of that because we checked before. So now we have the buffer index. So we can get the corresponding pixel. And what we now need to do is to get the pixel, calculate into it the error diffusion that we have, with respect to the Floyd-Steinberg matrix we have here, and then we are more or less done. So let's see. First of all, we need to calculate not only the position we have now calculated the position in our image buffer, but what we need to do as well is we need to calculate the corresponding position where I add in this one-dimensional Floyd-Steinberg array. I could have made it a 2-dimensional vector or something like that, but that is always more inefficient in memory, so I tend to not do that. So let's call it like diffusion index, di. And the diffusion index, it's more or less calculated in the same way. So what we are doing here is we are taking the dy and we are multiplying it with 3, as we know that this thing has 3 columns per row. And then we are adding to that the dx, but we are shifting dx up by 1 to make it positive here. So because it goes from -1 to 1 and we want it from 0 to 2. And this should already suffice to give us the needed value. And dx might be negative here, yes. So can I just say this one might be negative as well? Mismatch types. Expected U32 found I size? What? Wait, what? Oh, because, okay, after we have done that as U size, okay, we can convert back to U size. No, U32. U32. Yeah, okay. So now we have those two informations. So what we can do now is we can actually do something like buff I, and buff I equals the value of buff I. So this would be the red value plus some sort of calculation there. And this is now the calculation of this error diffusion. So what we actually put in here is something like we take the error, like we have QE, the red channel of it, and we multiply it with Floyd-Steinberg at position DI. Cannot find value buff. Yeah, I've called it buffer, haven't I? Maybe I should have renamed it. Yeah, I guess. Wait, why is that? The type F32 cannot be indexed by U32 because, okay, we need that as a U size, don't we? As U size, because all the indices are U size. Yeah, okay, makes sense. Okay, so now we actually are okay here, but the problem is that the resulting image here has a U8 as a color component, and we are actually calculating this one here with floating point numbers. So what we need to actually do is we need to round that one, and then we need to clamp it to a value between 0 and 255. And I guess I need to provide that as F32s, maybe in this syntax. I like this syntax better. And then we want to convert it as a U8, because then we are sure that we can. So this might overflow in the calculation. We might go out of the byte color space here. So we need to clamp it. We want to round it to eliminate everything which is not an integer, and then we want to clamp it to make sure it fits there. And then we can convert it back actually. And what we now have here, we need to do for all of the color channels. So we need to do it for I, we need to do it for I plus 1, I plus 1, I plus 1, I plus, sorry, here is it, it is 2. And then of course we need to adapt that RGB. And now that we have done that, actually, if I don't have any bug in there, and I'm sure I will have, but if I don't have, we have implemented error diffusion dithering. So let's see what actually happens here. Attempt to add with overflow. I thought as much. There's always a bug. So interesting. Attempt to add with, okay, wait a second. What did I do there? Let's see. Oh no, I did something wrong here. I need to I need of course to round and clamp the whole computation here, not only the error diffusion part. So what I actually need to do is something like this, I guess. And here as well. And yeah, and then I need to do this as F32. Yeah. And yeah. So let's try again. Because of the whole value can of course overflow. That's taking quite some time. Why is it? It was kind of slow. open output PNG. Nice. And as you can see now, this image is actually really nice. And it only consists of 16 colors. So we did everything right, I guess. And when I zoom in, you can actually see the dithering pattern created here, can't you? And down here in the in this floor here. And it's quite astonishing. I should have saved the non-dithered one with 16 colors, or here, for example, that is really nice. There you can see it really nice as well. The dithering creates really nice images there, because now when I put them at this scale level, when I put them against each other, let's maybe put away the console for a second. Okay, I can't easily do that. Okay, so let's put that there, and let's come on. Then I will move this to another screen. There you go. And now if you look at those, they are more or less identical. The color space is a little bit different, which you can see. So if I'm no, that's not really good. So the color space is a little different. If you're looking here at the floor and here at the floor, you can see that the color nuances are a little bit different. This can happen, of course, because we only have a limited palette. And if some kind of color nuance simply isn't in the target palette, then we can't create it through any sort of dithering. So the color space, the looking of this is a little bit different. But otherwise, this is a perfect example of what we can do. We could even limit our colors further to maybe we find quickly, let me close those again and let me get my terminal back here. Can we quickly find some sort of 8-color palette, maybe? 8-color palette. Pixel art. And maybe use Google for that, because, yeah. What is that? Okay. Those all don't look like really nice, equally spaced thingy. We could try something like that and have fun with that. Okay, let's try that. Let's see what actually downloads. Yeah, we can we copy those? We can copy those. Let's try that. Let's actually try that and only use 5 colors, which are kind of RGB and 2 different grayish counts, as we have a quite yellowish image. I'm not sure how this will turn out, but we will see. We will see. So let palette E, which is a vec of UA, vec of colors, let be equal to vec. And let's put in the palette there, and let's do more or less the same that we did before. We just remove this and make color from, and we put a 0x in front of that, and then we do that, and then we do that, and then we should actually be finished. And now let's take a look at, maybe let's move our output to PNG to output 16 PNG, I guess. And now let's do this and create an output 8 PNG, and let's just take a look at how this looks. I'm really interested in seeing how this actually looks. And output 8 PNG. Yeah. I feared that because it simply can't really do the yellow with this palette. But even though we only have those 5 colors and the color space is completely wrong, it still looks kind of okay-ish if you assume that there is or if you accept that there is no yellow actually in there. What we could actually do is, can we simply put into this palette, let's simply add one yellowish color there. So like color from 0x. And now let's see what happens there. So it wasn't even 8 colors, it was 5. So now we have 6 colors. So let's see. With a slightly optimized palette. Open, output, 6. And this already looks so much better with only one more yellow tone in there. Yeah, but you can see how all of this works, and that it actually does its job quite well. I will adapt it to the palette then that my e-papers understand, and maybe in the future even integrate this. Maybe even in a video together with you. Tell me in the comments if you would be interested in something like that in a short application, which then will create those images on the fly maybe and serve them to my e-papers in the format that those e-papers need, because they need a specific pixel format then. But yeah, I guess this is the end of our stream here, and yeah, I want to open this one up again because I really like how this actually turned out, because this is actually really the dithered image and it looks fantastic. Of course, the mileage varies there between different kinds of images. As you have seen, the palette must somewhat match the image. And there are actually algorithms there to find the perfect palette. If you are not constrained by the palette itself, but only by the number of colors, for example, you can obviously try and find a mostly perfect color palette to dither and match your image. But that would be a completely other topic. Yeah, I hope you had as much fun as me implementing this, and I will put the code up on GitHub. And yeah, thank you for watching, and I hope to see you in the next one. If you are interested in it, don't forget to like and subscribe, and see you then. Bye!